Hey, hi everyone. In the last video, we did steps 1 and 2 for particle in the box. We wrote the Schrodinger equation, we solved it, and got this answer here. This is the mathematical form for particle in the box wave functions. And in this video, we're going to do step 3, which is to interpret. I'll tell you what that means. So whenever you solve Schrodinger equation, you get wave functions and energies, and the first thing you should always do is sketch the wave function. So I'm going to do that, and what you can see is that this equation tells me that the wave functions are sine functions. So here's my box. This is x. This is 0 to length L. And specifically, I see that the wave functions here are associated with a quantum number n, and they're just an integer number of sine humps. Right? So if n is equal to 1, I'm going to put psi sub n, I get one hump. At x equals L, it's 0. At x equals 0, it's 0, and I get one hump in the middle. If n is equal to 2, again, it's 0 at the edges. It's also 0 in the middle. If n equals 3, you can kind of start to see the pattern. You're going to get a wave function that looks like this. So they're just sine functions, and you should be able to sketch any particle in the box wave function that we identify. We interpret the wave function in terms of its square, right, which is related to, psi squared, which is related to the probability of finding it. And so again, here's x, here's 0, here's L. If you square these functions, here's what you get. Right? And equals this one. That should be touching 0, but I'm not a good sketcher. That's n equals 2. Here's n equals 3. 3 humps. Okay, so let me start to point out a couple things to you about this. The first is this point right here. I wanted red. So this point right here, where the wave function is 0, is called a node. And nodes are important, right? So formally, they are locations where the wave function is equal to 0. It has to switch from positive to negative. So at the edges here, it does not count as a node because it hasn't switched sign. But we have nodes here. And what you'll see is that as n, the quantum number increases, the number of nodes increases. Specifically, you'll see that in this problem, the number of nodes is equal to n minus 1. Right? So as n is increasing, the number of nodes is increasing, the wavelength is decreasing, and the energy is going up. Right? Inconsistent. There's some other weird things too. So here's a little more formal plot of these wave functions. If I'm in the lowest energy state, n equals 1, right, you see that the particle hangs out in the middle. It does not spend any time at the edges of the box. And this might be confusing to you, because remember, if this was a classical system where I had a particle which was contained in some box, it would just ping back and forth, ding, 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 ding. And you would expect an even distribution. This is classically what you would expect. when we have a quantum mechanical system, it doesn't ever touch the edges of the box, which might raise an interesting question. How in the world does it ever go back and forth, right? It never touches, yet it's somehow going back and forth. The situation gets even weirder because here it hangs out in the middle of the box. If I give it a little bit more energy, so I promote it to an n equals 2 state, look at this. In this case, now it's never in the middle. The probability of finding it is again 0 at the edges, but it's also 0 in the middle. So somehow it gets from one side of the box to the other without ever going through the middle. Give it a little bit more energy and the situation changes. You see all of this weird behavior. Right? Students often want to know, well, what's going on? How does that happen? And the answer is, I don't know. Fundamentally, this has to do with the wave nature of particles. Right? It is not a unique particle. It has some wave-like character. It is spread out over space. And this is what the distribution of that looks like. Quantum mechanics is weird. It is. And I hope that you enjoy thinking about some of these things. Right? That's what makes it fun. Sketch wave functions, know how to interpret them. I'm going to stop here, and in the next video, I'll tell you about energies.